So for detecting the error, whatever message the sender is sending toward the receiver, so the sender will use some additional bits along with the information bits. These additional bits will help to identify the errors, to detect the errors at the receiver place. So we are going to call these additional bits as a redundant bits. So that is the redundancy. So how many additional bits are needed based on the method that we are going to use? So a simple method is a parity-based error detection method. So in the parity method, so one additional bit is used per row or per column. One additional bit is being used, one redundant bit is used per row message or per column message, depending on row-based information if we are using to transmit then one additional bit per row as redundant bit. If the transmission is based on the column wise, then one redundant bit per column. So that is being used in the parity method. So there are two types of parity checking methods are used. Simple parity per check, so one bit per row likewise. Or second one is two-dimensional parity check. Depending on the requirement, so can be used. We will discuss both these methods based on the parity technique. So when we are using the parity technique, we can use one of the two parity methods, either odd parity or even parity. So odd parity, including the redundant bit, the number of ones in the message, including redundant bit, is equal to odd number of ones. Where if you are using the even parity mechanism, so the number of ones in the message with including parity bit is number of ones are even. So if even number of ones are there in the transmitted information, that is original message plus redundant bits together is even, then it is called even parity. If they are odd parity. So depending on the requirement, we can follow any of that. But for understanding purpose, whatever examples we are going to discuss, we will be using even parity method during our examples. Okay. So for example, in this, so we are using a 4-bit message. If you are using 4-bit message, so total 16 possibilities are there for the message using the 4 bits. 4 zeros, 3 zeros, 1, 0, 0, 1, 0, 0, 0, 1, 1, likewise, till 4 ones. These are the 16 combinations, 16 possible messages, 16 possibilities for sending a 4-bit message. For this, if you want to use the parity for error detection purpose, we will be appending one extra bit on the LSB side. So the value of that bit, depending on the number of ones. So as we have already discussed that, we will be following in this particular discussion even parity mechanism. So the appended bit or parity bit, what we are going to decide is based on the number of ones in the message. So to become even. Say in the first example, first message, 4 zeros. So no ones are there means even. So parity bit becomes 0. Together equal to even number of ones. The second combination 0, 0, 0, 1. So single one is there. Odd number. We have to make it even. So for that reason, we are adding a parity bit as 1 on the LSB side. We are appending parity bit 1 on the LSB side to make the entire message to be transmitted equal to even number of ones. The third message 0010, again single one is there, odd number of ones. So the parity bit that we are going to add is 1 to make total even. Text message 0011. So already even number of ones are there. So the parity bit that we are going to append is 0. Likewise, so with every possibility of 4-bit message, so this table is giving us the possible parity bit, the possible redundant bit, the value of possible redundant bit, so that entire message become having number of even number of ones. So in that way, this particular simple parity check method is being used. So this is the concept will be used in the error detection mechanism using simple parity check. Okay, so here I want to send this particular data, that is A3, A2, A1, A0, 4 bits. Now what I have to do, I have to add one redundant bit on the LSB side of my message. My message is A3, A2, A1, A0. And the R0 is my redundant bit. I'm appending at the LSB side. So these are the 5 bits to be transmitted from the sender side. So this is the sender's place and this receiver's place. So the sender has to send 4 bits of original message with one redundant bit. So total 5 bits to be transmitted. Now from these 4 bits, whatever the parity bit that is being generated using the generator should generate an appropriate value of parity bit based on the number of ones present in the original message. If the number of ones present in the original message is equal to even, then the generator should generate parity bit as 0. If the original message is having number of ones odd, then generator should generate the redundant bit as 1, so that altogether will be equal to even number of ones. So that should be the task of generator. So it has to generate the appropriate parity bit with a value either 0 or 1 based on the number of ones present in the original message. So our interest is we want to use even parity mechanism. So the message to be transmitted should have even number of ones, including the parity bit, such a way that generator should generate the parity bit. That information will be transmitted to the receiver. Then the receiver will receive the, say, 5-bit message. Out of 5 bits, 4 bits are original message, and the 5th bit, which is appended on LSB side, is a parity bit. Now all these 5 bits will be verified using the checker, parity checker. So generator is a parity generator. Here the checker is a parity checker. The result from the parity checker must be 0. If the result, that is S0, is 0, that means whatever information received is correct, no errors are there. Then the parity bit which is appended on LSB side will be discarded. Remaining original message will be accepted and further processed if the output of the checker is 0. So information received is okay, no errors. So the parity bit is being discarded and remaining message will be accepted, and it is being stored in the appropriate buffer for further processing. Suppose if the checker output is non-zero, that means there is something wrong in the received information. There is an error in the received information. The error may be 1 bit or multiple bits. Okay, then the received information will be discarded. Received information will be discarded. Then again, the receiver will send the negative feedback, negative acknowledgement, and the receiver will be asking for a retransmission of the same frame. That is how this error detection mechanism is used in the simple parity mechanism by both sender and receiver. Okay, so and this we will see one example. So what will be the generator circuit and what will be the checker circuit. That we will see first, then we'll go to the next. So for that, we'll go to a blank. Just remember the generator means by using the original message, the parity bit will be generated. The checker will verify the received information for errors. Okay, so in this case, now, so what we'll do is, suppose I want to send a message, say my A3, A2, A1, A0 is equal to, say, 1011, for example. This is the message I want to transmit. So what is the redundant bit I want? So how the generation of parity bit is taking place at this point? Okay. So my generator circuit is, we'll draw a generator circuit simply by using the XOR gates. So 4 bits are there. I'll be using 2 XOR gates in the first level. And the second level, I'll be using 1 XOR gate. This is my R0, my redundant bit. So I may be using, say, A0, A1, A2, A3. So what is the message I'm going to send is A3, A2, A1, A0, R0. This is the message I'm going to transmit. So what we want to use even parity mechanism. Okay, let us use even parity mechanism. So this is the generator circuit. Okay, this is parity generator. So XOR gate 1, 2, and this is 3. Now the message that what we want to send is say 1011. So A3 is 1, A2 is 0, A1 is 1, A0 is 1. Now what will be the output? So if the first XOR gate inputs are 1 and 0, output will be 1. As we'll know the functionality of the XOR gate, if inputs are different, output is 1. If inputs are same, output will be 0. Okay, so if we are talking about 2 input XOR gate, exclusively OR. That means if the inputs are opposite, output will be 1. If inputs are same, output will be 0. That is applicable for a 2 input XOR gate. Now for first XOR gate, the inputs are opposite. They are different, so output will be 1. Second XOR gate, the inputs are 1, 1. Inputs are same, so output will be 0. Inputs are same means both the inputs may be 0, both the inputs may be 1. Then output will be 0. Now, third XOR gate, the inputs are 1 and 0. They are different. Output is equal to 1. Okay, so R0 generated will be 1. Now, what is our original message? A3 is 1, A2 is 0, A1 is 1, A0 is 1. So the original message is having odd number of ones. But what we want, even number of ones should be. So R0 must be 1. So R0, what is generated is 1. So R0 is. Now this is the message we need to send. Okay, this is the message we need to send. And this message will be received at the receiver end. Then receiver will verify, will check whether the received message is correct or not. Whether the received message is correct or not. So how it is being? So the receiver will have the checker circuit. The checker circuit will have again the XR gates. This is one XR gate. Another XR gate. This is another XR gate. And sorry, this. Okay. So this is XR gate 1, 2, 3, and this is the fourth XR gate. Right? So let us we'll try again. So we'll try again this particular one. And we are going to have one more XR gate at the checker point. We have one XR gate extra. This is the fourth gate. This is A3, A2, A1, A0. This is R0, whatever is being received. Now this A3 is 1, A2 is 0, A1 is 1, A0 is 1, R0 also. Okay. If the same thing is received, let us assume that the received data is 1, 0, 1, 1, 1. Okay. 1, 0, 1, 1, 1. Now we'll find out whether we are going to receive whatever is there, whether there is any error or not. So this is what we are going to say is output is error. If this is 0 means no error. If this value is 0, so we can say, for example, output. If this is 0, no error. Or if it is 1, then there is error. Okay. If this is 1, right, then there is error. So let us see whether we have any errors or not. So first XOR gate inputs are 1 and 0, output will be 1 as inputs are different. Second XOR gate inputs are 1, 1, same, output will be 0. Third XOR gate inputs are different, output is 1. Fourth XOR gate inputs are, so R0 is 1, so fourth XOR gate inputs are 1, 1. So output will be 0. That means no error. Okay. So whatever result we are getting is 0 means whatever data is received is correct. Whatever data received is correct. Instead of receiving this, suppose if the data received is say 1, 0, 0, 1, 1. Suppose if this is the received, instead of this 1, so instead of receiving 1, 0, 1, 1, 1, instead of this 1, suppose we have received a 0. Okay. Now what will happen? So let us draw the diagram again. Second XOR gate. Third XOR gate. Fourth XOR gate. 1, 2, 3, 4. So this is A3, which is 1. This is A2, that is 0. So A3, A2, A1, A0, R0. Then A1 is also 0. A0 is 1. So 1, 0, 0, 1. R0 is also 1. 1, 0, 0, 1, 1. 1, 0, 0, 1, 1. Now if you see the first XOR gate inputs are different, so output is 1. Second XOR gate inputs are different, output is 1. Okay, so this one is coming as input to the fourth XOR gate. Now the third XOR gate inputs are 1, 1, output will be 0. Fourth XOR gate inputs are 1 and 0 different, so output will be 1. So if it is output is 1, so there is error. Because if you observe the data received is odd number of ones. We are supposed to receive even number of ones, but we have received odd number of ones. So that means there is error. But where exactly the error is, we don't know. Maybe we have received 1 instead of 0. Maybe original information, this bit might be 0, but we have received 1. Or the second bit, maybe this might be 1, but we have received 0. Or third bit, maybe 1, but we have received 0. Fourth bit, maybe 0, but we have received 1. And maybe the final redundant bit, maybe 0, but we have received 1. Now get into that where the error is. Error could be anywhere. Error could be here, or error could be A3, or error could be A2, or A1, or A0, or R0. So that is why using this mechanism, we can be able to detect error, but we cannot able to correct the error. Okay, so that is one. Suppose if we got 2 errors, even number of errors, 2 errors. Suppose we get a multiple errors. There are 2 errors. Okay, this is one error, and say instead of 0, maybe we have received 1. Okay, here instead of 0, we have received 1. Instead of 1, received 0. Now let us assume that this is the information we have received. Then, so A3 is 1. So A2 is 1. So this is also 1. Then A1 is 0. A0 is 1. R0 is 1. Okay. Now first XOR gate inputs are 1, 1. So output will be 0. Inputs are same, output will be 0. Second XOR gate inputs are 0, 1. Output will be 1. Okay. Then third XOR gate inputs are 0, 1. So output will be 1. Fourth XOR gate inputs are 1, 1. Output will be 0. That means it is saying that there is no error. Okay. And even if we observe, so we have received even number of ones. 1, 2, 3, 4 ones we have received. Out of 5 bits, 4 ones we have received. So that means we'll think that there are no errors. There are no errors. But originally speaking, there are 2 errors. Okay, originally speaking, there are 2 errors, A2 and A1. Both these bits are having errors. Okay, instead of 0, 1, we have received 1, 0. But the circuit is saying, checker is saying that no errors. So this is a problem we are going to have with parity check. Odd number of errors will be detected, but even number of errors will not be detected. Suppose 3 errors are there, odd number of errors will be detected that there is an error. But 4 errors are there, will not be detected. We'll say that no error. Okay, likewise. So using the simple parity mechanism, we will be having a problem of non-detectable even number of errors. Only odd number of errors will be detectable. So that is one biggest problem in this parity checking mechanism. Okay. So that is why this is not preferred in the communication because so it is not able to detect even number of errors. So that is a problem in this.